All right, so we are excited to kick off our first panel on longevity and aging. This panel is supposed to be moderated by Dr. Joao Pedro De Magalhães. However, he's having some issues with connectivity. So we're going to go ahead and get started with Professor Nir Barzi-lie of Medicine and Genetics at Albert Einstein College of Medicine. And he's also the director of Einstein-Institute for Aging Research. Welcome to the panel today.
Thank you. Nice being with you.
And we have Dr. Eric Verdin, President and CEO of the Buck Institute for Research on Aging.
I wanted to say two things that are related to what you just introduced. First of all, aging has a biology. We know that. We know who's young and who's old. What people don't realize is that this biology drives diseases, but this biology is very flexible, and we can target aging, and we can delay aging, and we can, in certain examples, even reverse or here you are, Eric, and reverse aging. So this is one thing to know. But to make it more to the point of what you just presented, look, if aliens will land here in Central Park in New York, okay, right next to me, the first thing they'll have to figure out is who's ruling the earth. They will be confused if it's dogs or people, right? Because the people follow the dogs and pick their poops. But once they understand that, they say, just a minute, you didn't figure out aging? You didn't stop aging? Because, look, they came farther than Mars, okay? If we are going to Mars and we didn't solve aging, by the time we get there, we'll have cancer, we'll have cardiovascular disease, we'll never be back. Okay, and so when you said it's complex issue, you need team with different knowledge. Well, we're one of the team. We have to stop aging if we want to go anywhere close to Mars.
Thank you for making me laugh this morning. I think I have not heard the analogy about who's ruling the earth. Yes, maybe I'll speak about also an aspect linked to aging, which is has emerged in the past years, and particularly at the Buck. It's the concept of geroscience. Over the last 20 years, something has happened really unique in terms of our understanding of aging. That is, it has been now amenable to being studied by the tools of molecular genetics, which means that during the last 20 years, we've been able to identify a whole series of genes that do control aging. And that means that you manipulate these genes in an animal model, either using tools of the laboratory, such as making mutations or making mutated animals, or with small molecules, drugs that target unique proteins. What we see, first, we are able to increase lifespan. We are able to alter the rate of aging. And remarkably, along with this, the animals do not only live longer, but they also healthier. And this was something that was essentially unexpected, because what has happened during the last 20 or 30 years or 100 years for humans is that our lifespan has progressively increased, but along with this has come a increased rate of a burden of diseases that we call the chronic diseases of aging. And this is what actually makes aging not so appealing today. So the new understanding of this concept of geroscience is the idea that if you actually slow the rate of aging, you also protect against disease, or at least you compress the period of life that one spends afflicted by diseases. And this is something that's particularly exciting for today, because this is something that we can really introduce today. And here and his work on metformin actually are leaders along those lines.
One of the things, one of the studies I have is studies of centenarians, okay, of 100 years old. And I have 750 centenarians and their family. And one of the first thing we asked is, okay, do they get sick when everybody gets sick? And they're just sick longer? Or is their lifespan and health span goes together? Because it's important that we have examples from humans and not only from animals. And the answer is that they get sick 20, 30 years later than people at the same at our cohort. Okay, so they have an extended health span and lifespan, but more important, and that's what Eric said, they have what we call a contraction of morbidity. They are healthy, and then they are sick just we're sick years before we die, and they're sick just weeks or months, or 30% of them just don't wake up this morning. So the point is, we are built, probably we argue, but we have a capacity to live 115 years as we're built. Doesn't mean that we cannot change it in the future, but and we die before the age of 80. So there's a low-hanging fruits that we can use and tools we can use now to start making a progress. And there's a lot of longevity dividends if we live healthy and die soon after.
Yes. So one of the oldest therapeutic interventions that has been shown to control aging is the idea of calorie restriction. And calorie restriction is the fact that you take a laboratory animal and you restrict the amount of calories that you make available for them to eat to 20, 30, or 40% of what they would eat spontaneously. And what's been shown, so these are close to 100 years old observation, is that if you do this, the animals not only live longer, to 30, 40, 50%, depending on the strain that you study, but they also live healthier. So you see, again, the same dyad that we've talked about: increased longevity and increased lifespan, but also increased health span, concept of the healthy years of life. Now, so because of this, there's been a lot of interest in trying to understand how does it work? What are the nutrient sensors that the body has that allows it to detect when nutrition is actually a bit defective? By the way, we today have the opposite of this in the US. Right now, we have an epidemic of obesity, which does exactly the opposite. And there's lots of evidence that obesity today leads to a contraction of lifespan and health span as well. So in our search for understanding the pathways that actually link nutrient sensing to longevity, a number of targets have been identified, and one of these is called a TOR, target of rapamycin. So this is a protein that is conserved in almost all organisms. It is inhibited by a drug called rapamycin, which by itself has a really interesting story. And lo and behold, if you actually treat animals with rapamycin, you see a dramatic increase in lifespan, even when you treat animals late in life. Now, this has generated a lot of excitement about potentially introducing this in humans, but also some trepidation, because rapamycin is actually used in the clinic at high doses, and it induces immunosuppression. So the concept now is to use rapamycin at lower doses and try to see if it will increase lifespan and health span in humans. And I believe there are companies that are actually exploring the possibility of generating what we call rapalogs, which are rapamycin analogs, and trying to test them in the clinic.
So, and I hear you were talking about rapamycin and rapalogs, and so I mean, let me introduce myself. So my name is Joao Pedro De Magalhães. I'm a professor at University of Liverpool and also CSO of Centaura, which is a space biotech company. So I guess I assume you've been talking about some of the latest breakthroughs and developments in this very exciting field. Which specific companies, for example, you were talking about companies working on rapalogs, Eric. I mean, is there some specific companies there you are very excited about?
Well, there are a number of companies that are at different stages that are developing analogs of rapamycin, and as a word of caution for a new field like aging research, the first clinical trials actually that was conducted testing rapamycin failed. However, that should not detract us from continuing. And I know, without going into the specifics of these individual companies that are actually pursuing rapalogs, there are a number of them. And there's a key problem is that there are two TOR proteins, or at least two complexes, TORC1 and TORC2. And there's a growing evidence that TORC1 is actually the complex that you want to inhibit. So there's a lot of focus on trying to understand or identify specific inhibitors that target that pathway more than the others. And along rapamycin, I think one thing that might be interesting to explore is also so rapamycin is a so-called calorie restriction mimetic. So a drug that mimics the state of calorie restriction. It might be interesting to hear from Nir about his work on metformin, which is another one of the calorie restriction mimetics, and what this might mean for humans.
Mm-hmm. Yeah, sure. So Nir, do you want to develop on that?
Yeah, but I want to again frame it for the benefit of our hosts here. We're telling you that aging is flexible. There's lots of drug and lot of promise. The problem is that the regulatory forces, like the Food and Drug Administration in the United States, hasn't have aging as an indication, or hasn't have aging as a preventable disease. And what we are doing now, we are leading a study that's called TAME, or Targeting Aging with Metformin, where we take the drug metformin as a tool to prove to the FDA that aging can be targeted. And not going to do that, okay? The healthcare providers don't have to pay for a drug. And if they don't pay for a drug, pharmaceuticals are not going to jump in and have better drugs, combination of drugs, and really start making much more of an impact. And so just briefly on metformin, metformin is a drug that was used in the 1950s to prevent flu and malaria and other infectious disease. And then it was found that it lowers glucose in diabetic patients. And long story, it's been the first line of treatment of type 2 diabetes with billions of years of use by patients, where it was discovered that people on metformin don't get diabetes, get cancers, don't get cardiovascular disease, Alzheimer, and even die less, have less mortality than people without diabetes. And so there's a lot of clinical data to suggest that. I just want to mention the most exciting thing that happened in metformin this year. 9 studies around the world showing that people on metformin all over the world had less hospitalization and significant less mortality. I mean, 2/3, 67% prevention of mortality. So I'm just giving you not a hope, but a real promise for something that we can start with. And metformin is generic and cheap. Everybody will be able to take once we prove the concept. But more important, so many good new ideas there. We need the FDA to understand that aging is preventable. And the diseases of aging are preventable.
Yes, no, that's. I mean, it's fantastic. Your trial of rapamycin in terms of proof of concept that we could do a clinical trial for aging, which would be a real breakthrough and a real blazer in terms of doing these kinds of trials that we will need for other compounds and other interventions.
Right. Exactly.
And yes, and I guess because I think so. Metformin I think extends lifespan in mice like 5-7% if I recall correctly. So is that kind of what you would expect in humans? And I mean, likewise, rapamycin I think like 15% in mice. And so I mean, the question is, I mean, what would be your expectation in humans in terms of actual longevity gains?
Well, we have to be careful. So first of all, I think Eric framed it right. It's about health span. I mean, look, if we target health span, we target longevity, right? But we pretend it's a side effect. I didn't want to live longer. I just didn't want to live healthier. Well, too bad. You live longer. But we have to be careful. Metformin shows you how you have to be careful with mice. Not everything works in humans the same way. I would argue that there's a huge clinical data from the UK that shows that people with diabetes on metformin had 17% less mortality than non-diabetic. That's more than the 7% of extension lifespan in rodents. Okay, so we don't have to assume that we know the magnitude necessarily. We expect, based on data, that metformin will increase health span by 2-3 years in our study. Okay, that's a good start. That's more than any disease that you can stop right now. If you stop cardiovascular disease, you're not going to get 3 years because people will get Alzheimer and diabetes and cancer because we never treated aging. Yes.
So, I mean, because the way I see this is that we have, so at the moment we have lifestyle intervention. I mean, you can exercise, you can eat right, you can do, all the things that I don't do enough, for example. But then, and that can give you some health and longevity benefits. But then the way I see it is that, okay, in the next stage of, let's call it the longevity revolution, we're going to have pharmacological approaches. We're going to have drugs. And that's where Rapalogs and metformin comes in, and other compounds. I'm sure, that there's quite, senolytics perhaps, although, there's some research on that. So, and that's a second stage. And then the way I see it as well is that we're going to have a third stage of more radical approaches, things like gene therapy. So, for example, with Centaura, we're working on artificial chromosomes. I mean, we're working on it as a technology in with multiple applications, but one that, I would certainly like to apply for aging and for rejuvenation and for more radical approaches. So, let me ask Eric, are there any radical approaches that you think could pan out in the end of even reversing aging in humans?
Yes, there are a whole series of things that are being considered, but I want to sort of push back a little bit, because I think lifestyle is really one area that fascinates me, because this is something that we can do today, and it is not generally appreciated to what degree your lifestyle actually affects your longevity. And there's been a long-standing debate. How much of your longevity and your health span is determined by what you've inherited in terms of genetic materials from your parents versus what you actually do, how you decide to live. And the recent data indicates that 93% of your health and lifespan is actually determined by lifestyle factors. And lifestyle factors means a whole series of things that under your control. That includes nutrition, that includes sleep, that includes stress. It includes exercise. And I think there's a growing and amazing science that really shows to what degree you can modulate and gain this extra 10 to 20 years. We see, for example, human populations in different countries having actually quite different lifespan and health span today, going from 78, what it is in the US, to close to 87, where it is in Japan. And one could argue that even in those populations in Japan, for example, not everyone is living sort of an optimal lifespan. I think that what this does to me is really points to what is today the limit in terms of what we can expect. And I would predict that if everyone in Marin County, where I live, just north of San Francisco, is longest living county in the US. Average lifespan is 87, which is by itself remarkable. And I can tell you a lot of people exercise and have a healthy lifestyle, but not everybody. And so this signifies that if everyone would be optimized, we can probably expect an average lifespan of 95. And this is today. Now, compare this to what we have. This is already a remarkable achievement. Now, there's a lot of work ongoing in many laboratories about artificial chromosome, gene therapy, and I think this will be the next stage. And it's hard to predict exactly where we're going to be going with this, but I can tell you a lot of work is going in many laboratories pursuing these directions.
Can I add to Eric? And I totally agree about lifestyle, except that Eric, you also, I don't know if you treat patients now, but I'm in diabetic clinic every couple of weeks, and them to exercise and diet, and less than 3% do it. But I want to push Eric back on one thing. Look, people who survive cancer therapy, because we give them chemotherapy and radiation, they're aging rapidly. In fact, the kids are, they get heart attacks at age 35. People who have HIV get age-related disease 10 years earlier. People who are disabled or on wheelchair and they cannot move and they eat more, they need help. I would say that poor people that have no access to good nutrition, don't do exercise, maybe you need to give them metformin and you'll improve their healthcare because it's cheaper than building gyms around them or something like that. As I said before, space. If we want to go to space, we need to form aging. So I think it's the interaction, like always we said, the lifestyle and drugs that we'll need. But I want to answer your other question, Pedro, about the future and can we actually stop aging more significantly? And you know, you can take a sperm of a 70-year-old man and an egg of a 50-year-old woman, and we actually measure their age, okay? And we can form a baby, right? And the first cells of the baby divide, and guess what? They don't remember the age of the parents. We all start at zero again, okay? We figured out how to do it for this instance. It's largely an epigenetic programming, and I didn't, you know, I'm not going to explain what it is, but the question is, can we imitate it? Can we think on the future that every month we'll go to a therapy that will kind of erase our aging, and we can be at 20 and stay maybe at 20 for longer time? I think it's kind of how we're looking at the field to progress with just this example as a flavor.
Mm-hmm.
All right, so just a quick time check. I want to see if we can open it up for any questions to the community. If you have questions for this panel, please go ahead and raise your hand using the button on the right, and we'll go ahead and unmute you and bring you to the stage. In the meantime, please, Pedro, if you could go ahead and finish up with the last question on your side.
Yeah, well, so I thought just a very quick note on what Nir was saying is that we know at the cell level we can rejuvenate cells. So with the Yamanaka factors, with cell reprogramming, we can take cells from a 90-year-old man or woman, and we can rejuvenate it. We can bring them back to a embryonic stage. So, I mean, we don't know if that's going to work at the, you know, if we're going to be able to do a therapy that does that to a whole human being. But we know at the cell level we can rejuvenate. We can rejuvenate people, and that is, I think, that's a remarkable from a conceptual perspective. And I think there's obviously a lot of technical and engineering hurdles to overcoming that, but something that says that in theory we can rejuvenate.
All right, so I want to thank this panel.
Thank you, and thank you guys.